The purpose of this lab was to use the motion of a falling object in real life to demonstrate Newton's second law and the momentum principle. This was done in two different ways, with two separate models. I recorded the motion of a pack of 4 coffee filters falling directly downwards against a flat surface. As you can see, for my calibration, I simply taped a ruler to the blank white wall behind the stick to use as a measure of distance. The important axis was the y-axis as I was tracking the downward motion, so I assumed, for the purposes of my lab, that the motion on the x-axis is negligible. This is the tracker output for the y position versus time graph. For the first model, only the effect of the earth on the coffee filter was taken into account, so the gravitational force, as you can see, was the only force acting on the object for the model. This is the Python code for the initial conditions of the ball. We include the ball mass, which is 4.8 grams, the ball position vector as obtained from tracker, and as you can see, the acceleration for gravity is 9.8 and the drag force of 0. This is the actual calculation loop for the y output as given by Python. As we can see, the F net is only equal to mass times the acceleration of the earth on the ball itself. Only gravitational force is taken into account. Here you can see me running the model code for in Python for model 1. This is how the ball would act if only the force of gravity were acting on it. As you can see, there's a slight or large overestimate of distance. When plotting the output of Python against the data series collected from tracker, you can see that series 2, which is the first model, against series 1, the set of dots, which is from tracker, show that there's a great deviation. Clearly something is missing. There must be another force acting on the coffee filters. In Model 2, we take into account the missing force, or the drag force, as exhibited by the air or the surroundings acting on the coffee filters to reach terminal velocity. If you look at the Python code for the second model, you notice that we factor in drag force as negative b some constant multiplied by the magnitude of the velocity multiplied by the velocity itself. Now this arbitrary constant b is determined on a trial and error basis of the model based on the final position of the ball matching up with the final position within tracker. For this model, we determined b to be 0.1798. Based on the data output from VPython, we again see this graph and compare as to Series 3, which is the model output for Model 2, as compared to Series 1. Now, these match up a lot better than Series 2 and Series 1 did. However, we can see that there's a little bit of discrepancy in that it underpredicts initially and then overpredicts slightly later. The reason that the second model and the data itself kind of level off and eventually develop a straight line indicating that no force is acting on the object and that there's a constant acceleration is due to the fact that eventually the object reaches terminal velocity. Terminal velocity is the velocity at which the magnitude of the drag force is equal to the magnitude of the gravitational force on the object. At this point, the net force on the object is 0 and the velocity is constant. Because b is a constant based on the shape of the object, we know that if the object had originally been thrown down with some initial force and a faster initial velocity, it would have achieved the same terminal velocity just at a faster in a faster interval.